We're now going to discuss direct current circuits. Our discussion will be limited primarily to resistors in various configurations, and then the basic operation of meters, voltmeters, current meters, watt meters, and then a good emphasis on RC circuits, resistive capacitive circuits, whether it's DC or alternating, especially the idea of transients, so how the conditions in an RC circuit change with time. So we're going to start with resistors in series. And series simply means that components are connected together in such a way that all the current has to go through each one of them. There's only one path. So that's obviously the case here between A and B. So the current. Now VAB, the voltage across there, is the IRs. So I, the current, times all the R. Well, specifically, it's the voltage VAX plus VXY plus VYB, the addition of those three voltages. But that's IR1 plus IR2 plus IR3, which is the same I times R1, R2 plus R3. And we have just defined the total resistance in a series circuit consisting only of resistors. Just add them up. And now in parallel you can see that they have multiple paths for current to flow. The current has options. It comes into A and says, well, I can go this way, I1, I can go this way, I2, I can go this way, I3. And you will notice that there's a potential here and a potential here at B. So the potential difference between A and B is the same for each one of these three resistors. So each one has the same voltage across it. Resultant current is the addition of the three. So I is equal to I1, I2, I3. So VAB over R, current is voltage. The voltage across here divided by the total resistance is VAB over R1 plus VAB over R2 plus VAB over R3, since each one has that same voltage. So you can see that this current is essentially enhanced as a result of having multiple paths through which to flow. So inverse R is the sum of the inverses, and that's a wonderful opportunity to use the 1 over x button on your calculator when calculating multiple resistors in parallel. And notice also that the resistance total, since 1 over R gets bigger and bigger and bigger, that means that this R is getting smaller and smaller and smaller. In fact, the resultant resistance is smaller than the very smallest individual resistance in parallel. Now, if the parallel circuit has only two resistors, we can just do a little algebraic operation, multiply this by R2 over R2, multiply this by R1 over R1, and we get this form. So there is the resistance, if that's helpful. Not necessary. And now, Kirchhoff's rules. Number 1, the loop rule, says the algebraic sum of the potential differences in any loop, an entire loop of circuit, equals 0, which is a statement about the conservation of energy. Remember, potentials are energy per charge, so it's associated with energy. So when you add up all the potentials, really potential differences around the loop, which is the sum of all the EMFs and sum of all the IRs, they equal 0. That's it. Now, the other rule of Kirchhoff, the point rule, which simply says the algebraic sum of the currents toward any branch point, a junction, equals 0, which is a statement about the conservation of charge. You don't have a buildup of charge at any point in the circuit. The closest we get to that happening is in a capacitor, but that's not considered a point in the circuit. So sum of the currents equals 0. Corollary to this idea is simply that the currents into a branch point or a junction equals the current out. Whatever goes in must go out. And that's it in brief. And now let's look at some of the rules for applying these principles. Okay then, rules and guidelines, conventions for the basic Kirchhoff rules we just defined. First, choose any closed loop in the circuit, the network of loops, and go clockwise or counterclockwise, your sovereign choice, adding the EMFs and the IRs until you're back where you started. The EMFs, how do you deal with them? Well, consider them positive if you go from minus to plus inside, because you're rising in potential. Consider them negative if you go plus to minus inside, because you're dropping in potential. What about the IRs? Same idea. You're going to consider them negative if you go in the direction of I, because when you go in the direction of I, you're dropping potential from one side of the resistor to the opposite side. So it's a drop in potential. It's a voltage drop. And plus, if you go opposite to I, if you go against I, from the front side to the back side, so to speak, from this side to the other side of the resistor, you're going to rise in potential. All right. So you assume a current direction through a particular element. As it gets more complicated, you don't necessarily know. Just assume it and go with it. If wrong, in the end, your results will be correct if they are positive. Your assumption will be correct if it turns out to be positive. If the current turns out to be negative, all that happened is you chose incorrectly. And it's not always possible to know ahead of time, so that's okay. Then, if necessary, choose another loop, obtain a different relation between the parameters you're trying to discover, and continue till you get as many equations as there are unknowns. And then, once you have that, solve for the unknowns. And you will be a happy camper in addition to being a successful problem solver. With the real simple series circuit, let's use Kirchhoff's rules to determine the current in the circuit. Now, we don't actually need to use Kirchhoff's rules here, but it's a good initial practice example. And we have current flowing like this. We know that's true because the 12 volt, which is bucking the 4 volts source, wins out and drives current counterclockwise. So let's go counterclockwise, then we'll go clockwise also. We're going to analyze it this way. So we have from A, since current's flowing this way, we have a drop. So it's negative 4 times I times R. This is the resistance times the current. Then we hit the battery. And is it a drop or a rise? Well, because of the way we're going from plus to minus, it's a drop. So minus 4, minus 7I, 7 ohm. Now, a rise of 12 volts, so plus 12. And then minus 2I, minus 3I. We've come back, we've come full circle, we're back at A, so all that's equal to 0. So we have 16I plus 8 equals 0. I is a half an amp. We just solved for it. That was pretty easy. Now you could have done current is sum of the voltage divided by the resistance. 12 minus 4 is 8. 8 divided by total of 16 equals a half. So that works as well. Just a simple application of Ohm's law. Now let's assume the current goes clockwise. And so we're going to analyze it clockwise. So I just showed that here. So ignore this for now, the direction. And let's assume the current's going around like this. And how we'd set up the equation. We would have, going in this direction, a drop of 3I, and then minus 2I, minus 12, minus 7I, plus 4, minus 4I equals 0. Giving us minus 16I minus 8 is 0, and I is negative 0.5 amps. The negative sign here tells us that the actual current direction is in the opposite direction of the one we chose, which is going clockwise. I'm sorry. The one we just chose now is clockwise. So we know it's actually counterclockwise. So that all works. Let's consider momentarily the power of the sources. The output power of the 12-volt source. Okay, just considering the EMF source itself. Now, it supplies power to its own internal resistance. Well, the output of the supply, then, to the rest of the entire circuit, including its own internal resistance, EMF times I, 12 times 0.5. That's the current passing through. So 6 watts total delivered by this EMF source to the rest of the circuit. The 2 ohm, the 3 ohm, the 4 ohm, the 7 ohm, and the rest is going into the battery. And we'll see what that is here. The power into the 4-volt battery. Well, now I'm looking at the whole battery, including its internal resistance. I squared R plus EMF times I. So that's 0.5 squared times 4 plus -4, because it's a drop across here, times 0.5, which gives us 1 watt from the internal resistance. It's a dissipated power, producing heat, and then 2 watts across the 4-volt EMF, but that 2 watts is negative, because it's kind of like potential energy. This electrical energy is being converted into chemical potential energy. So that's kind of consistent with kind of like the charge is doing positive work and the battery is increasing in potential energy.